Attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. I apologize for being late, but my computer decided to crash and reboot the first time I started this up. So I just got finished rebooting my computer because admittedly I accidentally booted it into Linux the first time, which doesn't really work. I don't have it on Linux. I can't talk to you guys when I'm on Linux, so I had to reboot my computer again. So basically half the time I was gone, that was my own fault. But anyway, yeah, I apologize. We'll run until about 10 to 15 after to make up for lost time, unless, like y'all have to really leave at 9 o'clock, in which case we'll run until 9 o'clock and then we'll figure it out some other time. But yes, welcome back. I hope you had a good couple of days, and I hope you're ready to continue with Arduino, because that's what we're going to do. We spent Monday talking about what Arduino was, what you could use it for, sort of. We talked about what a microcontroller is and everything like that. And then we did a gentle introduction to 123D Circuit. Oh, nice, Caleb. Yeah, I got Ubuntu and 8.1. So you've definitely got me beat on that. Is it a Hackintosh, like is it Macintosh hardware, or is it a like a custom built computer that you've installed OS 10 on? Custom laptop, nice. But yeah, anyway, we talked about what a microcontroller is. Microcontroller is a programmable logic controller, but it's small, really small. That's SMOL, small. And you can use it for just like, really, your imagination is the limit. We talked about all the random stuff that you could do, like, or really I talked about it. You could lock your door remotely if you have it connected to the Wi-Fi network at home, and you have an app on your phone that can communicate with that. It requires some extra work, but it's doable. You can set it up to control like a quadcopter, or you can, a thing I was doing for a while, it was really super simple. No, that was a Pi actually. But you could do it with an Arduino where it could, I had power outages for a while. Didn't really build anything. I sort of showed off the features of 123D Circuit, but today we're actually going to build the first thing, which is a blinking LED, which is really, really simple. No, you should be fine, Cohen. Just set up a 123D Circuit account, and you'll be more or less caught up. Because I'll spend some time reviewing the controls and stuff like that for it as well. But yeah, there was a period of time where my power was going out fairly frequently, and so it was a Raspberry Pi, but you could do a similar thing with an Arduino. I had it send a message. Well, I had it basically email myself and say that my power was back up. So I plugged it into the wall, and as soon as it booted up, it would send an email to myself letting me know that my power was back up. So when I was, out at the coffee shop or something like that, and I got an email saying that my power was back up, then I could come back home. Because I had horrible luck with power in my old place. People were crashing into power poles, and trees were falling onto transformers, and it was all bad. Anyway, yeah. So we'll 123D Circuit. We'll by way of reviewing 123D Circuit, we will build our first circuit with the Arduino, which is going to be just a blinking LED, and it's exactly as simple as it sounds, although it's a good way to look at like how the hardware and the software interact with one another, and how you can combine the two in order to do something a little bit more complex than just like a simple circuit. The thing that we're going to build is totally possible to build with a circuit. It's totally possible to build with software. However, combining the two, we can do less work in each of those fields in order to accomplish the same thing. If we wanted to build a circuit that blinks with hardware, we would have to set up some sort of, capacitor and diode assembly to ensure that, like, that the LED would blink every so often, and electricity would flow in the right direction. And uh, if we wanted to do it on the software side, we would have to include something that sends out the correct voltage, and we would have to hard code in, like, the way it talks to the hardware. And anyway, with an Arduino, it's easy because a lot of that stuff at the very, very, very lowest level is already done for us. So you can search for 123D circuits, or you can search for circuits.io. Circuits.io is the newer version of 123D circuits. Excellent. Glad to hear it, Cohen. So if you go to 123D circuits, their website, it'll redirect you to circuits.io. Your choice. If you're more comfortable going to 123D circuits and doing the redirect from there, then by all means, feel free. You're going to have all of your designs here. It automatically saved my unnamed circuit from October 11th, which was Monday. I must have closed it later that night because I definitely, it was the 10th was definitely Monday. But anyway, regardless, this is the circuit that I want. Go ahead, click Edit, and it's going to bring up our circuit from last time. So again, this was our super ridiculously simple circuit. We used the Arduino as nothing more than a source of power for our circuit. If I click Run or Start Simulation, the LED lights up. It doesn't do anything though. It does nothing. It just lights up. Because right now we have power running from the 5-volt prong, peg, hole, whatever, on the Arduino, which just sends out a constant stream of 5 volts of power. Electricity. How do you do what? Well, we'll get there. We'll get there. I'm just going over what we did on Monday. But yeah, so this was just the ridiculously simple version of what we had. Now what we're going to do is we're going to build a very similar circuit, but it's going to incorporate some code from the Arduino so that the LED blinks. If you've seen something like this before, well, this will probably be review then. So what I'm going to do is I'm going to delete everything somehow, some way. Oh, right, because we're running a simulation. Okay, so the base level on a blank 123D circuit, you're going to be looking at the breadboard. And if you guys remember, you can use R and Shift R to rotate it. Like so. R rotates it clockwise, Shift R rotates it counterclockwise. Pretty simple. You guys remember how breadboards work, right? How it's got the how similar rails or rows are connected to one another. How do I? Okay, so let's go back to circuits.io. If you're on the main page, you're going to want to click on Create, and then you're going to want to click on the Open Electronics Lab Hub. Oh, you're fine. You're fine. I did sort of skip a couple of steps there. And then you're going to want to click on New Electronics Lab on that page. And that should bring you up to the design page. Or the design, I guess design page, where we were before. So remember, Create, Open Electronics Lab, create new electronics design or something like that. And remember, the mouse wheel zooms, scroll the mouse wheel to zoom in and out. R and Shift R rotate. You can use the arrow keys for fine-tune placing, or you can just click and drag. Well, not from there, but you can just click and drag in order to move things around as well. So what we're going to need is we're going to need an Arduino, obviously. We're going to need a red LED, and we're going to need a 330 ohm resistor. Were you able to find it, Cohen? Rotate with the R button. Just R on your keyboard, or Shift R to rotate in the other direction. Perfect. All right, so let's go ahead and add those components in. Now, as you might remember or expect, if we want to add components, we have to use the Add Components menu. So in the upper right-hand side, we've got a little plus sign and the word Components. Go ahead and click that, and it will bring up a whole list of stuff. And we can actually expand this list so that we can see more of it at a time, but I'm going to bring it down to about halfway so we can drag it out as well. So we're going to want a resistor, and we're going to want an LED. And then we're going to want an Arduino. In fact, an Arduino Uno will serve our purposes perfectly, and it actually has, I believe, the same setup as one of the SparkFun Red boards. So I scrolled down to find it. If you're not sure, you can go up here to the search bar and you can type in Arduino, and you'll see all the Arduinos that they have for selection. So I'm going to bring up the Arduino Uno R3, I believe revision 3. And perfect. So now that I've got those three things, I'm just going to go ahead and click that Components button again to take it away, or get rid of it. There we are, 123D circuits.io. Yeah, you know, the digital recreation of the Arduino. You can also, what is the yellow thing on the left? I'm not sure what you're referring to. The resistor. Oh, this thing? That's a resistor, yeah. That right there is a resistor. Sorry, I don't think of it as yellow, so that's part of the reason why I got a little confused there. But yeah, that's a resistor. All right, excellent. So, again, this is how we're going to build our circuit. And again, we're going to need a 330 ohm resistor. Now remember how resistors can come in a whole bunch of different resistances. You can have a 1,000,000 ohm resistor. You can have a 15 ohm resistor. You can have a, yeah, you can, mega ohms. You can have a, you know, a 400 ohm resistor or a 5,000 ohm resistor. So we need to be able to make sure that our resistor is the proper resistance. And the problem with that is in the components list, it's just listed as resistor. It doesn't have a specific rating to it or anything like that. But here's the thing. That's because we can change the resistance of this resistor in 123D circuits, which is pretty useful. It allows us to, rather than just selecting from a list of a whole bunch of different resistors, we just change the value of how much it resists, and we've got exactly the resistor we need. Right now, this is, I believe, a 1,000 ohm resistor. This brown band is 1, the black band is 0, and the red band, I believe, represents 2. 10 times 10 to the 2. 10 times 100, which makes it 1,000. I believe that's what, yeah. Anyway, you can also read the bands on a resistor in order to be able to tell what its resistance is. It's something that it's something that you don't really use a whole lot unless you start messing around with electronics a whole lot more. Hence why I was sitting there wondering precisely what it is, and thankfully I was right. If we click on the resistor, so it's got this blue outline, we get this window up here, if you remember, the properties window, which will give you a couple of options, name and resistance. So its name is 1 because, you know, names are useful. And its resistance is listed as 1 kilo ohm, so 1,000 ohms. What we can do here is we can manually type in another value. We want to make this 330 ohms. So I'm going to type in 330 and click the drop-down menu to select ohms instead of kilo ohms. Not milliohms, kilo ohms. And there we go. We've got 330 ohms. Orange represents 3, so 3 and 3, and then brown represents 1, so it's 1, or 10 times 10 to the 1. Yeah, so 10 times 10, which makes 100. 33, 3.3 times 100 makes it 330 ohms. We can do the same thing with the LED, except we can just change the color. I'm going to make a green LED, because why not? And then we've got the Arduino. The Arduino itself, we're not going to worry about for now. We're actually going to just sort of move it up into the side in order to get it out of the way. And we are going to hook up our components first. So those of you who were here on Monday and might remember, why is that bad? Why is me hooking it up that way not ideal? Yeah, well, you weren't here on Monday. Think back. That's fine. Think back to why how a breadboard works. Oh yeah. Well, let's hear it. Oh, okay. Well, you tried. Okay. So remember how everything on the same rail on a breadboard is all connected? So like all of these are considered on the same rail. All these holes are considered on the same rail, so they're all connected to one another underneath. And remember how electricity is lazy? It always takes the path of least resistance. So we might have a whole bunch of stuff hooked up. Like we might have our resistor hooked up on this, and generally everything looks okay. And there might be let's just go ahead and there might be like a jumper off here and a jumper off here connected to something else. So like ostensibly we have a completed circuit, because you would think like, all right, so electricity is going to travel along the jumper, it's going to go down into here, it's going to travel along the rail, it's going to go up into the LED, back down, over onto the resistor, and then across this way and out the other side. You would think that. You would think that. However, we run into an issue. What really actually happens is the electricity comes from the jumper onto the rail. It goes down and up into the LED, and then when I say electricity is lazy and it moves the path of least resistance, which do you think would have less resistance, if we traveled along the resistor or if we just traveled back and went back up and around the LED again? Yeah, back. So we just go back and it would travel up around the LED again, and back and up around the LED again, back and up around the LED again, back up around the LED again. And the LED would light up. It would get super bright, and then it would get brighter and brighter and brighter and too bright, and potentially, depending upon how much power we have going into this, the LED would pop, which is cool and dramatic, but not exactly something we want to really do with this right now. That's what a short circuit is. A short circuit is when you have when the electricity is traveling along a shorter circuit than you intended to, hence the name short circuit. That is really where the origin of the term comes from. So that makes it pretty straightforward, at least. But that's why we don't want to have it hooked up like that, because then we cause LEDs to pop, and that's how we cause, electronics to catch fire and dispel their magic smoke, and then they stop working, and, it's not really what we want. So what we do is we ensure that our components are not connected on the same rail. And what I mean by not connected, in this case, the beginning and the end of the resistor should be on two separate rails. Same with the LED. Yeah, that's something you definitely want to ensure to make sure that you don't have a short circuit. So now we've got our resistor hooked up, our LED hooked up, and as you can see, the resistor and the LED are hooked up on the same rail, which means they're connected to one another. Perfect. Now we need to hook up the Arduino to it. So our power is going to come in and then run through and go out the other end. Remember what these two vertical rails are for? Excellent. So what are they for? Okay, I'll give you a hint. Look at the top of the rails. There are two symbols. The top and the bottom of the rails. Yeah, plus and a minus. So these are designated rails. They don't actually supply power or, ground anything, but they are designated rails for you to hook up like a common power and a ground. That way, rather than having to plug in your power to everything, like let's say, whoa, we can put curves into the jumpers. Okay. Let's say we had like a whole bunch of these all hooked up, and we wanted to, connect power to them. Well, the long and inconvenient way to do that, whoops, the long and inconvenient way to do that would be to hook up power to each of these things. And that's not even really possible because I can only plug in one thing in there. You could also, I guess, jump from one to another one, but again, if you want everything to run in parallel, that's not really going to work either, and we'll go over parallel and all that stuff in a bit. But the alternative is we can hook power up to this plus rail. Now the plus rail, this entire plus rail, has the power from the Arduino, and then we can plug each of these things into the plus rail. Likewise, we can hook the minus rail up to the ground on the Arduino, and then we can hook up the other end into the minus rail so that they're all plugged in. Yeah, it provides a common ground and a common power. So I'm going to go ahead and color these jumpers so that they're more in line with common electric coloration thing. I can't remember what it's called right now. But anyway, if you're working on something in your house, chances are if you see a white wire, it's going to have electricity running through it. If you see a green wire, it's going to be a ground. If you're working on electronics, if you see a red wire, chances are it's going to be what's called the hot wire. It's going to have electricity running through it. If you see a black wire, it's going to be the ground, that kind of thing. Oh, how did I copy them? I used Control-C and Control-V. That works in a lot of things, and those things are your friend, especially when you're coding. Copy and paste. They make your life a lot easier. You can, alternatively, you can select them, and I believe you can, no, right-click is not enabled. Oh well, Control-C and Control-V will do it. You can also use the delete key to get rid of things. The delete or the backspace key, I believe. Yeah, you can also use the backspace key. And you can use Control-Z to undo stuff. Control-Z is probably more of your best friend than copy and paste are. Control-Z works everywhere, or Command-Z. And it will, if a program has support for it and they do it properly, it will undo the last thing you've done. Oh, is how you select more than one thing at once. Yeah. Oh, grab. Yeah. You can shift right click or you can shift left click. Both of those work. For some reason they had left click and right click. Should I make that? I do want you to plug your 13 into the plus rail and your GND into the minus rail, and you can create the jumpers just by clicking. Just left click once and then left click again in order to create the endpoints. So now I got this whole big thing, but I'm going to make this a little bit less cluttered. There we go. So now I got this whole big thing. I've got the 13 hooked up to the plus rail is hooked up to the LED is hooked up to the resistor is hooked up to the Control-C and Control-V will make copies, but for now we're just going to have one copy. The resistor is hooked up to the minus rail, and the minus rail is hooked up to the GND on the Arduino. Let me see if I can rotate the Arduino so that the wires aren't crossing like crazy. Yeah, that looks a little bit better. So just to verify that this works, let me hook it up to the 5 volt and start the simulation. Okay. So based on that, I know that I have this backwards. I do that a lot. I apologize. So the resistor should be hooked up to the plus rail, and the LED should be hooked up to the minus rail. And if we start the simulation, the LED lights up. So I'm going to take it away from the 5 volt, so now we only have it hooked up to the 13. Pin 13 should be plugged into the plus. The resistor should be plugged into the plus. The resistor should also be plugged into the anode of the LED, and the cathode of the LED should be plugged into the minus. And the minus is plugged into the GND on the Arduino. So there you go. That's the circuit. Now we need to actually program the Arduino so that it does neat things like make it blink. And that is where the programming side of things comes in. Now we're going to start learning about how to program with an Arduino. We're going to skip installing the software for now because we can actually do the software entirely through, 123D Circuit or circuits.io, depending upon your preferred name. And we're just going to go ahead and delete all of that because that's actually the code right there for making the LED blink, but we're going to walk through this step by step. So click on Code Editor and then just delete the code that appears in there so that it's empty. And you should just have line 1. So every single program, all of them ever created forever for Arduino are based on two things. They're two functions. And functions are simply just blocks of code that do stuff. The first function is setup. The second function is loop, I believe. Yeah, loop. So those two. Every single code ever created for an Arduino needs to have void setup and void loop. It's just how an Arduino's code is structured. Essentially what happens is when an Arduino first starts up, it runs everything that's inside of setup. Once it's done running setup, it then goes into loop and runs loop over and over again forever until it loses power or you reset it, in which case As soon as it has power again, or it starts up again, it's going to go into setup once, and then it's going to go back into loop again forever. So that is the basic structure of an Arduino's code. It's going to have a setup and it's going to have a loop. Now it can have other stuff on top of that, which we're going to start exploring as well. But at its base, it's always going to have setup and it's always going to have loop. And like I said, these are called functions. Functions are they're just blocks of code, really. It's like, let's see here. I'm trying to think of a good analogy. How about those? This is not the best analogy, but this is the first one that comes to mind. How many of you have played those, like, or read those Choose Your Own Adventure books? Okay, one person. All right, so not many of you. In essence, a Choose Your Own Adventure book has this kind of thing where it goes like, okay, so yeah, kind of like Zork, but like in book form. They go like, okay, so now, you're standing in front of a castle and you have to find a way to get inside. And it goes like, if you want to get inside by swimming across the moat, turn to page 93. If you want to get inside by climbing the walls, turn to page 74. Stuff like that. And then you might be on page 25, in which case you skip to page 73 because you try to climb the walls, or 74. And then it's like, okay, so you climb the walls. Now, if you want to go left, go to page 50. If you want to go right, go to page 52. That kind of thing. And so you get sent to sort of different areas of the book based on your decisions. Now, when I say like go to page 74 or go to page 53 or something like that, you can think of those like the function calls. Because maybe, for instance, there's a lot of times in these Choose Your Own Adventure books, there are dead ends. There are places where you can lose. So like, it'll be like, oh no, your adventure ends here, book over, the end. And there might be multiple different places which can send you to that page if you make an incorrect decision at any point along the way. That is how these can be similar, because you can call a function. You can tell a function to run multiple times within a program. You can tell a function to run 1,000,000 times within a program. You can tell a function to run, maybe once or never, depending upon your program. But you can write like 5 lines of code in that function and then call it 1,000,000 times, and it'll run those 5 lines of code 1,000,000 times. Just better than writing 5,000,000 lines of identical code and having it run over and over again. But I digress. At any rate, if we want the code to do something, if we want to give it a command to do something, we need to place that code inside of a function. Lines of code can be outside of the functions as well, but usually those are just reserved for like variable declarations and stuff like that. So what we're going to do now is we're actually going to, we're going to declare a variable. So that's going to go outside of our it's going to go outside of our functions. I just typed int space LED capital PIN equals 13. Well, why did I do that? Well, like I said, I declared a variable, right? But that doesn't really mean much unless you know exactly what I'm trying to do here. So variables, as you guys I'm sure are aware, are basically slots in memory that hold information that you've reserved for later use. So in this case, I created a variable to hold a number, in this case 13. So anytime I want to use this variable and its number, how do you go up? uh, like in the text? Oh, I just selected the beginning of the void setup line and I hit enter a couple of times to move it down. And I moved everything beneath it down as well. But yes, okay, so did that help, by the way? All right, excellent. So what I did is I reserved a slot in memory to hold on to the number 13. So in case I needed to use that number 13 later, I could. Now, why specifically 13? Well, again, that's where the programming comes in. That's where us as programmers determine what is the most useful thing to go in there. For us, we wanted to store the number 13 because we wanted to have easy access to the pin number. And this is not the redundancy that refers to the thing you use in an ATM, but the number for the pin that we're plugging our jumper into. So in this case, pin 13. We want to keep track of that number. Now the second part refers to the name of the variable. Anytime we want to access the variable's values or change it, well, either to read it or to change it, we need to refer to it by name. In this case, we gave it the name LED pin because that's the pin that's sending power to the LED. So LED pin. Pretty simple, right? And then this first bit, int, that is the type of the variable. There are multiple different types of variables, but for now we're using one that holds whole numbers called integer because, integers are whole numbers. So all of these things together, including the semicolon at the end, create like the full declaration and initialization of a variable. We're creating an integer variable called LED pin, and we're immediately setting it equal to the number 13. The semicolon at the end is like the period at the end of the sentence. Anytime you have a statement in code, a thing that has like a command, in essence, this can be thought of as a command because we're telling the computer to create a variable of type integer, call it LED pin, and set it equal to 13. So anytime you have like a command that actually tells the computer to do something, Declaration of Independence, nice. You got to have the period at the end of the sentence, or in this case, the semicolon. I can't tell you how many times you'll be freaking out over something that's not working and pouring through your code, only to realize that, in a caffeine-induced coding binge at like 3 o'clock in the morning, you forgot to put a semicolon somewhere. So, again, if it's going to be a standalone statement that is an instruction to the computer, it's got to have a semicolon at the end. And I'll go ahead and just start typing this out here because the font is bigger, so it'll be easier to see. So you might notice that I have two sets of brackets. I've got parentheses and I've got these curly brackets. The parentheses are how we know that something is a function. So void setup and then parentheses, the parentheses say that this setup is a function. Same with void loop. The parentheses tell us that it's a function. There's more that the parentheses do, but for right now, that's the easiest way to sort of to regard the parentheses. If you see parentheses, you are looking at a function. You're looking at either a function call or a function declaration. The curly brackets are how we're able to tell what's inside of that function. So if we want code to be part of void setup, like to go inside of void setup, we would put code inside of the curly brackets. By contrast, code here is part of loop. So as you can see, we can assign code will be a part of a function. And when I said, functions can execute blocks of code as many times as you want them to, the code that's inside of setup will be executed every time setup is called. The code that's inside of loop will be executed every time loop is called. If we were to write a custom function, which we can do, no, not the stuff in here. I just wanted to. That's for illustration purposes. But make sure that you've got parentheses and curly brackets as well. So we've declared a variable, right? We haven't done anything with it. So what we're going to do is we're going to fix that. We're going to put something inside of our void setup. And again, I want you guys to put this into the circuits.io code window. No, you don't need semicolons after the parentheses. And that's an excellent question. That's because this void setup and the void loop, you can think of it as being like paired with the curly brackets. And in that sense, it's not really a standalone statement like a lot of these other things we're going to be writing. These are entire blocks, so that they won't have semicolons after them. But yes, so we are going to type something into void setup. It's going to be pin mode LED pin output. Oh yeah, there you go. That's how you make it blink. Nice. So I added a single line of code to setup, right? Now what does this do? Interesting. Okay, let's take a look. Pin mode has some parentheses after it, does it not? There's stuff inside the parentheses, but it's got parentheses after it. What do you think that means? Yeah, it's a function. So just like how with variables we have to declare them and then we can call them at any points, this whole void setup bit right here, this is a declaration for a function. This right here, pin mode, we're calling a function, one that's already been declared for us by the lovely people who created the Arduino. And that's totally valid. We can call functions inside of other functions in this case, it's necessary. In many cases, it's really, that's kind of how code is just sort of stringing a bunch of functions together and throwing them all inside another function. But yeah, so what we're doing here is we're calling a function that's already been declared. In this case, the function is called pin mode. We're giving it LED pin, in this case, our pin 13 number, and then this all caps output is, well, in essence, what we're doing here is we're setting pin 13 to be an output pin. We're making sure that electricity is sent out of pin 13 instead of it waiting for electricity to come into pin 13, which is a pretty important distinction because, I mean, electricity is not going to be going into pin 13. Nothing's going to be going into pin 13 because the other side of this is going to be the ground. So we want to make sure that we're sending electricity out of pin 13 so that it does all the cool stuff that we want it to do. So we wrote that one line in setup. And again, remember, You got your semicolon at the end here because we're calling the function, we're not declaring the function or defining the function. Pin mode LED pin output, semicolon, boom. Void setup is done. Now we're going to make the magic happen in void loop. Now in loop, we need to tell this thing to turn the LED on and off. So we can do that with something called digital write. And once again, what do you think digital write is? Well, it's a function, isn't it? Yeah, exactly, it's a function. Also, based on the name, you might guess that we're asking the Arduino to send data out on pin 13. Again, we know it's pin 13 because of LED pin here. What do you think the high refers to? Yeah, exactly. Well, yeah, but basically, yeah. So like you remember my explanation of digital versus analog voltages on Monday? I'll draw the graph again. Yeah, in essence, analog can be anywhere from no to full power. Like it can be zero power, it can be full power, it can be anything in between. With digital, with digital, it can either be no power or it can be full power, but it cannot be anything in between, which is why you get these vertical lines, because it switches from no power to full power in an instant and back. So if we look at it, as a graph over time, we have these vertical lines where it switches from one to the other. But since we can think of it like a graph, it can also help clear up why we use the values high and low. So when we say high, we're sending power. When we say low, we're not sending power. So digital write LED pin high. We're sending electricity out on pin 13. Then we're going to include this right here, delay. Let's go with yours, Mateo. We'll make it 500. And then we're going to say digital write LED pin low and delay 500. What do you think delay is? Yeah, that's exactly what it is. It's how long it waits. Why do you think it's 500? Well, I'll just go ahead and... Yeah, exactly. Wait to execute script. I'll just go ahead and tell you. It's because an Arduino measures time in thousandths of a second. So if I were to put delay 1000, it would be 1 full second. Delay 500 means half a second. So basically, if we were to run this code through line by now, we go into loop, we turn on the LED, we wait half a second, and then we turn off the LED, and we wait half a second. And because it's loop, and it always runs loop, always and forever, as long as it has power, it's going to run back to the top of loop, it's going to turn on the LED, it's going to wait for half a second, it's going to turn off the LED, it's going to wait for half a second. You get the idea. Now, we have to tell the Arduino to turn the LED off again, because computers are dumb. So far we've established that electricity is lazy and computers are dumb. Aren't you glad you are thinking about becoming an engineer? Just have to deal with all of these wonderful things. But yeah, so we have to tell it to turn the LED on. The computer is not going to assume, or in this case the Arduino, is not going to assume to turn it back off because it doesn't know any better. So we have to be explicit and tell it to turn it back off. A lot of times when your computer or your Arduino or whatever is doing dumb stuff, it's because we as programmers, a lot of times it's because we as programmers made an assumption on some part during the process that the computer did not also make, the processor did not also make. So you got to be sure to break things down into as small and explicit steps as possible. In this case, we tell it to turn on, we tell it to wait half a second, and then we have to tell it to turn right back off and wait another half a second before turning back on. Otherwise, it's going to turn on for half a second and it's going to turn off so quickly we can't even see it before it turns right back on again. It's just going to blink. That's the blinking noises, because that makes sense. Anyway, I'm going to go ahead, and with that, that's going to be our completed code for Arduino. I'm going to upload and run it. As you can see, the LED starts blinking in half-second intervals. Hopefully, you guys have a pretty good idea as to why that's happening on the software side now. On the hardware side, we created a completed circuit, and on the software side, we basically coded it so that it sends a value through on pin 13. Now, it is 5 minutes after, and I think this is a good note to end this lesson on, especially because it gives us 5 minutes to do the poll questions before we run into 60 minutes exactly. And then I'll leave it open to question and answer time like we always do at the end of the class. If you have any questions, I'll be here. If not, you're more than welcome to head out and have a wonderful weekend, and we'll see you on Monday. So here we go.